the annual Peter Landin Semantics seminar of the FACS group. My name is Jonathan Bowen, chair of the BCS FACS group. I think I know most people here, and there are various people. We've got more people online than we have here. Things seem to be moving that way for people. It's obviously a lot easier to attend talks online, but it's nice to see some people here anyway. I'm sorry those of you who are online will be missing the wine, and we will drink your health after this talk anyway, and be thinking of you. So today we've got Edmund Robinson, who's worked at various places around the world. He's been at Queen's University, Ontario in Canada, but also at Cambridge, Edinburgh and Sussex. But since 1995 he's been at Queen Mary University of London, where he's been Professor of Computer Science. He's also been Head of Computer Science Department. We were commiserating about that earlier. Also merging computer science and electronic engineering, becoming head of schools. Glutton for punishment, perhaps. But anyway, so he's been based there for a while, and very nicely, he was there when Peter Landin was still there. So given that this is the Peter Landin Semantics Seminar, we're hoping to hear a few little anecdotes of Peter. As we know, that anyone who's met Peter Landin will know he was a great character. So perhaps we'll hear a few more of anecdotes about him. So the overall, well, the area of interest of Edmund is categorical logic and semantic of logical theories. And he's given a nice general title of Logical Relations and Mathematical Foundations. I advised a general title so he could talk about whatever he wants now. So we'll find out what he's actually going to talk about, and hopefully hear a little bit about Peter as well.
Well, thank you. So as you said, I'm at Queen Mary, and I thought I'd begin by kind of saying a little bit about why this opportunity means so much to me. So as you know, Peter worked at Queen Mary for much of his life, and what you see in front of you is the first of a series of rather bad photographs. But that's the building that we're currently housed in, and that Peter had an office in towards the end of his life. His office would have been at the far end, overlooking one of the remaining bits of the Jewish cemetery that the college is mainly built on. So you see this kind of fairly grubby university building that once used to have as part of our biology department, and now houses electronic engineering and computer science and a gym. So the stair tower goes up to our building, and I just want to zoom in a bit on this kind of archetypal, typical grubby university entrance, and zoom in just a little bit more. A few years back, we convinced the university that the building really ought to have a name, and that name ought to be Peter's. So the building I currently work in is in fact the Peter Landin building at Queen Mary, which, as you know, breaks the unbreakable law that any university computer science department has to be named after Alan Turing. So Peter was actually, I mean, as Jonathan said, Peter, I arrived in 95 when Peter was still working there, and I looked like a couple of rather bad pictures, but that kind of gives a picture of roughly what he looked like when I met him. And certainly his reputation, his presence was one of the reasons that I went to Queen Mary. And once I arrived there, for the first few years, I had about 3 years, I had the privilege of sharing a programming languages course with him. He was teaching a course on programming languages, and this being Peter Landin, it was not in any way a conventional programming languages course for the time. So conventional programming languages course for the time would go through, here's what an imperative language is like, here's what a functional language is like, and here's what a logic programming language is like, here's what an object-oriented programming language is like. And Peter's was not like that at all. And it was, I think, wild and eccentric, and probably anyone who, I mean, I think everyone who goes to university ought to get at least one course which is really weird and eccentric and inspiring, and that was Peter's language course. He spent so let's go back. So there on the right, you can just about see him leaning over the lectern and kind of grinning at the audience and really wanting to communicate with them, and that's absolutely what he was like in the lectures. So
I can assure you that the audience was laughing a lot at this. I was in the audience and co-organised this particular meeting. So it was a wonderful meeting. It's on video somewhere, and we must get it digitised.
So one of the really big themes of that programming languages course was that programming was a way of communicating between the programmer and the machine, and that one of the big things he was trying to do was to convince the students that you couldn't tell what a program meant just by naively looking at it. So there are lots of examples of instances of things where scope was, and if you used one approach to scope, you got one result. Another approach to scope, you got another result. Different orders of evaluation that give different things, and you learned that really the text was only part of the picture. And moreover, one of the things that he was trying to do was give lots of simple examples and to convince the students that they ought to go away and do experiments and find out what things were doing by producing minimal examples. And as students were, they were fairly resistant to that. But there's a picture of the kind of the notes that he was producing and gave to the students. So talking about programs supply different names to other parts of the program, blocks, stuff. Then over on the right, exercise. I think that is 10.13 and not 1013. So, assuming a language in which the following phrases are definition, give an experiment by context to determine something or other, intended to settle whether it's block or not. So he was very, very interested in describing what programs do, and should say kind of. So there were, I think the department had two kind of reasons for getting me involved in this course, and one was that it was this wonderful chaotic course that none of the students who came really at the time knew what they were getting, and they wanted an element that was more boring and kind of regulatory compliant or whatever. and secondly, they didn't quite trust him not to go completely off the rails or disappear. And they desperately needed somebody to carry the can in case he did. Which he never did. But Peter was really great. So he's very interested in describing what programs do. He's very interested in communicating things in very basic ways to his students. Quite skeptical about the advanced mathematical techniques and technologies that were creeping into semantics. So he's very polite, but not really interested in kind of high-level type theories or cunning category theory. And what he wanted was something that could be understood and used by the programming community. And in some sense, kind of that's the direction in which the semantics community that I'm part of has gone. I mean, when I first came in, and still kind of at the time people were still thinking in terms of proving programs correct, right? In some sort of absolute sense that you'd have a specification in the program and you'd prove that the program. And that's not at all where people are now. So where people are now is about doing formal reasoning, providing tools that in some way improve the quality of the code in code bases. So there's a much greater emphasis on practical things being practical, not doing everything, but they have to fit in with the development chain. One of the kind of the great pieces of work that we did say we, not really me, but came out of the department kind of a bit after Peter left, was the development of separation logic. And so that is something that's really not trying to do everything, but it's for example enabling you to say kind of that you're not going to follow null pointers on the stack. And that was developed, and the great thing about it was that it was developed to a point where it became push button and could feed into the code development processes for companies like Facebook. And so we ended up going to quite a lot of talks by Peter Ahern and Dino Di Stefano, at which they were talking about how important it was that you should be able to that you should be able to kind of run this thing in the time that the programmer would expect. Submit the code, they should get a response, that it shouldn't it was more important that you didn't provide too many false positives than that you tried to produce as exhaustive a list of possible bugs. the aim was to kind of get rid of enough stuff that you improved the end quality. So things have gone that way, and I'm not really, I'm afraid, going to talk much about the industrial stuff, but I'm going to talk about, take it in a slightly different direction and talk about the modeling techniques and trying to look at kind of how simple you can make the models, because a lot of the technology has become very complicated and we've lost sight of the underlying ideas. And part of the point of this talk is that if you do keep track of the underlying ideas, then it's, and you keep them simple, it's really helpful. And in fact, a lot of the academic publications don't do that, and so are obscure and hard to understand. So if you do want to, even if you don't want to reason about the complete behavior of a program, you've still got to provide some kind of formal model. And the language that we have for doing that is inevitably mathematics. That's because mathematics essentially is the language we use when we want to do calculations about things. Partly the mathematicians, you might not quite think that. So it's the language we use when we want to do the calculations, but the calculations are inevitably never about the actual system. So if you go back to the really earliest examples of mathematics, about things like how to calculate how many bricks you need to build a wall. And it's never a calculation about actual bricks, it's about sort of models of bricks, what they weigh or what they're used on. So they're about models of the system. And that inevitably raises a question. What happens if we use different models? Do we get the same results? Are there ways of showing that we might get the same results? And conventional mathematics is really good at doing analysis of a particular model and pretty bad at considering uniformity across models. There's relatively few stuff. Mathematicians don't take the modeling process particularly seriously. And one of the key, I think the key things that we have for doing that in a very simple and systematic way is this idea of logic, is the notion of logical relations. And what I want to do in this talk is to kind of give an introduction to logical relations, and I want to try and make the idea as simple as I can, as blindingly obvious as I can, as content-free as I can, so that I'm hoping is to make it seem obvious. And secondly, I want to show you that you can take those ideas and derive some standard notions of process equivalence. So I put logical relations as going back to about the early 1970s. So this is the first instance in print. There on the right, you can see the start of a paper lambda definability and logical relations, which I think is the first time the term was used in what I'm going to call print, by Gordon Plotkin. You see that it's TypeScript. And he says that it's an idea that's been around. He's talked to Mike Gordon about it, and also in Edinburgh at the time, and Robert Milne in his thesis. That was Cambridge at the time. Cambridge at the time, they later moved to Oxford. Used something similar for proving the equivalence of implementations of programming language. So it's absolutely, so Gordon is using this because he was interested in finding uniformity properties of lambda expressions, and he wanted to be able to say that anything which was uniform in this way was actually given by a lambda term. Didn't quite succeed in that. Robert Milne is absolutely in the area that I'm talking about. He was saying, got one implementation of programming language and another implementation of language. How are you going to relate the two to prove them? You get the same results. And it's something that's been, it's a technology that's quite widely used. So I went on Google Scholar and looked at, just to look at how many papers there were this year on mentioning the term logical relation. And there's about 1,300. Not all of them will be about, not all of them, it's a phrase that could occur in a more natural context, but if they mention Popple as well, it's a good bet they're talking about the kind of logical relations that I'm talking about. And there are about 800 plus listed. So it's a really, really widely used piece of technology at this point. And if you look through, they'll talk about, so this is, third paper down there is engineering logical relations for something or other in Conc, automated reasoning. But there are all kinds of using a logical relation for this, using a logical relation for that, stepwise logical relations, scripty logical relations, all kinds of things. But I'm going to start at a really basic level, a really basic level. So I talked about kind of having structures and models, and at a very basic level, kind of one of the things you might have is a structure that comprises just some basic entities that operate. So you've got basic things like something you call an A, something you call a B, something you call a stack, something you call an element. But you have just these basic entities and operations. So an operation that takes an A and produces a B. And then you have potentially models of that structure. So you say, got this entity which I call A, and I interpret it. And so I've tried to use blue for abstract syntax in a sense, and I've tried to use the red and the purple for different concrete models. So I'm going to interpret this. I'm going to give, say, a set A and a set B and a set of and a function between them. And I've got a red A and a red B and a red function. as one model, and I've got a purple A and a purple B and a purple function as another model. And I want to know when those two are similar. And an obvious thing to do is to say that I've got some kind of relationship. I've got a relation between red things and purple things. So the gold, the yellow, let's call it yellow. So the yellow here represents having a relation between my red interpretation and my purple interpretation. And I want to say these functions behave similarly if, when I give them related inputs, I get related results. So that's a very obvious idea, that you've got an idea. You've got so relation between inputs that says when this thing and that thing are supposed to represent the same concrete object. For example, the relation between outputs which says when that thing is supposed to. And these two functions are well behaved if our implementations of a similar function can be implementations of the same function. If when you give them related inputs, they produce related outputs. Okay. So I'm going to rewrite that picture slightly. So I'm going to take this as a diagram for relational composition, and I'm going to treat the functions as relations. Well, I compose this relation and that function, then that's always less than or equal to the composite that I get the other way around. So if I sorry, let me try and I have a red A related to a purple A and then apply F to it. That's the same. I could get the same pair by first applying F to the B and then choosing a related element there. So if I do the composition, this inclusion. Okay, and that's a nice picture because once you've done that, you can start putting things together. So if I have two diagrams like that, which represent, so here I've got a function from A to B and a function from B to C, and I've got an A to B and a B to C. So red A to B and red B to C, and a purple A to B and a purple B to C. Diagrams like that, relations across them. Then I can paste them together and I get a bigger diagram. So I can compose operations. But also, if I'm thinking of things in a different way, that this is a possible implementation. If I'm doing stepwise refinement, so I think this relation as being purple is a refinement of red. So my purple things are, so I'm gradually developing things. So purple things are a refinement of red. Purple is a refinement of red. Then, and I'm terribly colorblind. I hope that's green. Green is a refinement of purple. Then I can paste those together again, like that. I can just put them together, and I get purple as a refinement of red. So the squares push together nicely, and I get this refinement, and that's all coming out of kind of basic, simple relational calculus. The idea. Now I've given you this for functions that take one input because that's nice and simple to draw, but it's not limited to that. You could do it for things with more than one input. And so it's my function red F plays nicely with my function purple F with respect to these relations. If whenever red A is related to purple A and red B is related to purple B, then red F of AB is related to purple F of AB. So we've got this. And I'm going to say that the system of relations is logical with respect to these operations if the operations respect relations in this way. So I'm going to say that over on the left, we've got the structure. Over on the right, it's a model. So we've got a bunch of relations between the A's and the B's and the C's. And I want the interpretations to play well with respect to relations. So that's a very simple, very basic idea. Two things behave in the same way. So if you've got two different models and you've got relations between the fundamental sorts, they behave in a similar way if when you give related inputs to an operation, you get related outputs. Okay, so from the mathematical point of view, the kind of structure that I'm talking about is basically algebraic. It's what mathematicians call algebra. So you've got objects giving basic sorts, you've got operations between objects, and potentially you've got equations between operations. And the usual interpretation has object being a set and the operation being a function. And a big example of that, and I'm giving you a maths example, I'm afraid, is that. Is groups. So groups are standard piece of the mathematical toolkit. You've got a set, you've got three operations, you've got you've got a set, you've got three operations, one of them is a multiplication, binary operation, multiplication. Then you've got a nullary operation, which is an identity, and you've got an inverse. And then there are equations that say that the binary operation is associative, that the identity is a left and right identity. For the the binary operation, which we call multiplication, is associative, and you've got left and right identities. Sorry, the identity is a left and right identity, and inverse, when you multiply an element by its inverse, you get the identity in, if you do either order. So that's the kind of logical theory, and then what the mathematicians call a group is a model of that. Right? It's a set with those operations interpreted in it. So there I've put kind of a red group and a purple group. So that's what, if you go to a standard, very old mathematical text, that's what they say. A group is a system of elements with these operations. So models are actual groups, and I'm going to just say what happens if we have a relation between those two. When is it logical? Well, it's logical if I take a pair of red elements and multiply them together, and a related pair of purple elements and multiply them together, the results should be related. And if the red unit is related to the purple unit, and if I take a red G, which is related to a purple G, then red G inverse is related to purple G inverse. So the relations are respected by the operations. Let's just say relations are respected by the operations. And now, in the particular case that the relation is the graph of a function, so if f is a function red G to purple G and red G and purple G are groups, then the graph, what that's saying is that the graph of f as a relation between red G and purple G is a logical relation for the group operations if and only if f is what is called a group homomorphism. So that's the standard mathematical definition of transformation of structure. So when the mathematicians talk about a group being transformed into another group, they'll talk about group homomorphism, something that preserves that. And that is coming out of this kind of standard computer science, different interpretations of structure and preserving different structure. So it's kind of recovering a piece of standard mathematical technology, and that's a result that holds for arbitrary theories. So if I take any algebraic theory, anything which is given by operations and equations, the mathematicians will give me a notion of homomorphism to that theory. And we've got a notion of logical relation. And if something is a function, it's a logical relation if it's a homomorphism. Sorry. So this very kind of basic idea is generalizing something that the mathematicians have had for over 100 years. And is an absolute and standard part of kind of first year maths courses. So now I'm going to kind of just move on a little bit from that and talk about first order types. So first order types, that is essentially in computer science terms would be JSON XML structure. It's potentially lists of things, but certainly pairs of things, and alternatives, options. So we have products and we have sums. And so if we want to use more than just the basic object, if I start trying to reason about things, I'm going to want to be able to put things together in various ways. And basically I can put things together as a combination, or I can put things together as an alternative. So that's the and or, and there aren't many other alternatives. So if I have products, then the product of A and B. So a typical element of A cross B is a pair, AB. And I want to say that if I've got a relation from, sorry, oops, go back. I want to say I've got a relation from red to purple on the A and a relation from red to purple on the B. I get a relation on the product, really simply, by saying my A had better be related, my red A had better be related to my red purple A, and my red B had better be related to my purple B. So I'm just saying both of those have to be related. And similarly, if I've got alternatives, so this is A plus B, and a typical element of A plus B is going to look like either in left of an A or in right of a B. Let's lay over here. And there the rule is that the relation is they're both in left and they're related elements, or they're both in right and they're related elements. So it's the union of relations on the sum of the times. So that gives you a very simple way of extending to sums and to sums. And so we've got, I just looked at the time. Okay, so that allows us to deal with n-ary operations. So we've got two ways of talking about n-ary operations. One is that I can say it's genuinely an n-ary operation. We've got n different inputs, or I can say equivalently that that's the same as a unary operation, but on the product of the inputs. So kind of some way that's curried versus uncurried. moreover, you can amalgamate things, and having two operations then is equivalent to having a unary operator on the sum of the inputs. So if I take the group example, I've got three operations, and I can package them all together into one thing, one operation that takes as input an element of g cross g plus 1 plus g, and if it gets the g cross g, multiplies them. If it gets the 1, gives you the identity. If it gets the g, it'll give you the inverse. So I can package them all together into one operation. And that leads you to the kind of abstract way that the people doing algebra, coalgebra, package their structures. So they'll take a functor which gives you a notion of terms, the classification of the inputs that you can put into terms and operations, and they'll package that, gets packaged into a functor. And in algebra, you've got things going in one way, and then so terms produce results, and in coalgebra, you've got things going the other way, that elements can be decomposed into something of a particular term. So you can have multiplication and co-multiplication. So multiplication is for the group. Take two things, you product them together, and you get another element of the group. Or co-multiplication, you take something and you say how it is expressed as how it's expressed as a product of two other things. Break it apart in a canonical way. So a coalgebra is telling you how to break things apart so that you can apply things to the bits, and the algebra is telling you how to put things together. But if you're looking at it from this perspective, from the perspective that I'm trying to show you, then the notion of relational correspondence doesn't care whether you're doing algebra or coalgebra. They're just operations that take sums of products at one end to sums of products at the other end. Doesn't care. And at that level, kind of everything is still fine. Everything that I'm showing you is absolutely fine. Operations compose. We can use all the type theoretic operations that we want, and logical relations compose. So if we've got two relations which are logical, which behave well with respect to operations, we can place them together and get something that behaves well. Do the stepwise refinement there. There is no way I'm going to get through all this. So Gordon Plotkin was particularly interested in extending logical relations to higher order types. And there the idea is that if we've got a pair of types and relations between them, can we get a relation between the corresponding function types? And if you go back to an earlier slide, then you get a picture of how we can. Red function is related to purple function if, when we give them related inputs, we get related outputs. That's a relation on the function. That's the extension to the higher types. And if we do that, then application is fine. If we take related functions and give them related inputs, we get related results. That's what the definition just said. But also lambda abstraction is fine. If we have functions that take two inputs, and so binary inputs, and they're related, then when we lambda abstract on one of the inputs, we still get the function. I won't go through the detail. But at this point, things start to break down. And the way they break down is two ways. One is that other constructors preserve order on relations. So if you've got one relation included in another, and you apply the constructor to it, you get results that are included. And function space doesn't do that. It swaps the order on the first input. And secondly, the composition fails. And there's an example. So this is a really example. So I've got a red thing, so one operation. And my red thing, my red A just has one element, my red B just has one element. And the function between them is send that element to that element. And my green thing is just the same. Now, those two are, and sorry, in the middle, I've got the purple thing, which has two elements, the purple A, which has two elements, and the purple B, which has none. So here I've got a relation red goes to the top, and here are the relation green goes to the bottom. And here I've got just the empty relation. Now, if I compose that, that is not related to that. This composite relation is empty, that composite relation is empty, and that function is playing well with respect to that function because it's taking related inputs. There are no related inputs. To related outputs, there are no related outputs. By right empty set playing, this is absolutely fine. But I can't find a function here to sit in the middle and be related to them. Because here I've got two things, and there I've got none. So there is no function at all across the middle. So I can't make there be something in the middle which says in this function space, this function space, that's right, sorry. In this function space, that's related to something in that function space is related to something in that function space. So I don't get inequality in the composition. So that the compositionality fails in that way. But we do have an order inclusion, which means that if I do have related function which is related to a function there, and that function is related to something there, I can still paste them together and get a function that is related to something there. And that will let me do the stepwise, continue with the stepwise refinement stuff. So I get half of them. Okay, so things that's why people say logical relations don't compose. They half compose. Okay. I'm going to absolutely skip this and just talk to you a little bit about state transitions and bisimulation. Now, state transition system, the basic idea is that you've got a set of states and a notion of labeled transitions between them. We have S goes by an action labeled A to state S goes by action labeled A to a state S prime. And there's a notion of bisimulation, which says when two systems are similar, which is due to David Park and probably also bit Robin Milner. Park for automata and Milner for more general transition systems. So the idea is that if red S is related to purple S, and red S can do an A and become red S primed, then purple S had better be able to do an A and become a purple S primed, which is related to the red one. And similarly, the other way around. That if purple S can do an A and become purple S primed, then red S can do an A, become red S primed. A relation like that is called bisimulation. And we can formalize that, so we can say that our system is given by a function alpha that takes an action, a label, and a state, and gives us a set of states that we can get by doing that action. P-S, set of S. Sorry. And let's suppose we've got two models of that. We've got the red model and the purple model. And we want to know for what relations between sets of states is red alpha related to purple alpha. And first of all, it doesn't depend on the exact way that things are structured, because we've got a nice type theory here. So I could have this in curried form, I could have it in uncurried form, I can reorder the inputs, I can do all kinds of things. But as long as the things are kind of lambda calculus equivalent, I'm fine. But it does depend on how we extend the power set to relations. And the obvious possibility is wrong. So do not interpret the power set as functions from states to booleans. Do not interpret it as 2 to the S. Instead, interpret it as, so that's kind of the contravariant interpretation. Use the covariant interpretation. So for this, you say that the power set of S is the complete free sub-semi-lattice on S, which, if that is just mathematical garbage, means that you give me a set of things in the power set of S, and I will give you their union. Okay, so it's got arbitrary union operations. And you can write that down in terms of an algebraic theory. You've got unions indexed by any set X. You've got equations between those unions, and you've got a model of that. and that's that is kind of, you've got to kind of relax a bit. That is an algebraic theory. It's not the kind we're used to. It's got a proper class of operations, and a proper class of equations, and that will get the people who are worried about foundations a little anxious. But it's all right because there's only a set of operations for each set up to equality. So you do not need to worry. And then we can ask, what's the free complete semi-lattice in relations? So we say, what's the model of the same algebraic theory? We want to be able to take unions of things. What's the model of the same algebraic theory? And there's an answer to that. And that is, okay, sorry, let me go back. Given the relation between red A and purple A, R, we want a P of R between power set of A, red power set, and purple power set. And so I want to be able to say when a subset of A, subset of red A, is related to a subset of purple A. Sorry. And the answer is that I've got some subset of my original relation, which maps down on the left to U. If we project it, if we take all the left-hand components, we get U. And if we take all the right-hand components, we get V. So let me try and draw that a little bit. So if I've got U like that, should be in red, and V like that, I've got something sitting in the middle that projects down onto V in that direction and projects down onto U in that direction. And if I change the definition, that means that for every U in U, there is a V in V, which is related to it. And correspondingly, for every V in V, there's a U in U. And now when I turn the handle, that's exactly what's going on with strong bisimulation. So given S, given a relation from R to S and a red alpha and a purple alpha, I have that red alpha is related to purple alpha, if and only if whenever red S is related to purple S, then alpha of A and S is related to red alpha of A and S is related to purple alpha of A and S. And that means that when red S primed is in that, then there is a related purple S primed also in that. And that's literally S. Red S can do an A and become red S primed, and then purple S can do an A and become purple S primed. So it's saying exactly the same thing. So what that says is that we've got logical relations generating this standard Park-Milner notion of strong bisimulation. And that's something that was kind of known to the coalgebra community before, but not quite in those terms. They've not got didn't, I think, know have the way of building the the interpretation on relations. They just said, well, you've got this interpretation. It works like this. And then this is stuff that I've done with colleagues, that we were able to extend it to other forms of bisimulation. So there's a big concurrency community. They've invented more forms of bisimulation than anyone wants to be told about in one lifetime. And so there's weak bisimulation, branching bisimulation, semi-branching simulation, colors. And we were able to show that, for example, weak bisimulation, branching bisimulation, semi-branching bisimulation could be made to fit into the same framework. And the way that we were able to do that, I'm going to scoot ahead, is basically this. You take your original model. So you take your original model and then you modify it. You apply a transformation. You say, okay, for something like weak bisimulation, we've got these special tau actions, and which are supposed to be internal computations. And then we're going to change the model so that it respects that idea in some way. So in this case, we've saturated it so that you can do as many internal computations, much internal computation as you want, always. And if you do that, then what you find is that you recover the notion of weak bisimulation from this kind of structure. And the same sort of thing with branching bisimulation. And branching bisimulation is a bit different, because the idea is that you consider you might have a sequence of internal computations and then leading to a synchronization point, and then you do a visible communication. So the model is structured like that. That's in the original definition of, kind of implicit in the original definition of branching bisimulation. But if you actually build a model of transition systems that incorporates this idea, then the notion of equivalence that you get out is branching bisimulation. And that's, I'm not going to talk about probabilistic bisimulation, but I'm going to finish. I'm just going to say, I hope Peter would have appreciated the attempt to try and simplify some of this. Just to end, this is a very bad picture of the other end of the building. It's only one end of the building. And you can just about read over the top that says the Peter Landin teaching rooms. And
it looks like tea rooms from here.
that would be really appropriate. Now, until this has appeared with kind of mysteriously and suddenly appeared, start of 1 year. And until a couple of years ago, this actually read Bancroft teaching rooms, because the road just behind us is the Bancroft Road. Now, Queen Mary there's one kind of small problem with us having Bancroft teaching rooms. 200 yards away, it's not such a small problem, because 200 yards away, there is a Bancroft building. And Queen Mary Estates Department had clearly not been attending Peter's lectures on the dangers of ambiguity. Because every year we would have hordes of students coming up the staircase and trying desperately to find rooms which were not in our building, but were in fact in this very much larger building, 200 yards away. obviously the estates departments assumed that the average university student would be able to tell the difference between the Bancroft Road teaching rooms and the Francis Bancroft building, but not. And eventually they've used Peter to disambiguate their estate, and I think he would have been immensely tickled by that.
Yeah.
So thank you.
Thank you. We'll overrun a tiny bit. Are there any questions? I'll ask first locally.